Evet. Merhaba değerli katılımcılar. Bugün alanında duayen, dünya çapında isim yapmış ve çok önemli başarılara imza atmış bir hocamızı Profesör Doktor İlhan Fuat Akyıldız'ı ağırlamaktan büyük şeref duyuyoruz. Hocamız bir ömre o kadar çok başarı sığdırmış ki ben kendisinden biraz burada bahsetmek istiyorum. Kendisi 120 bine yakın atıf almış yayınlarıyla ve 125 aş indeksiyle dünya sıralamasında ilk 45 bilim adamı arasında yer almakta. Hocamız 2011'de dönemin Cumhurbaşkanı Abdullah Gül'den uluslararası üstün nitelikli çalışmaları nedeniyle aldığı TÜBİTAK özel ödülü de dahil olmak üzere çok sayıda ödüle de sahip. Hocamız 45 doktora öğrencisi yetiştirmiş. Bunların 30'u şu an dünyanın önemli üniversitelerinde profesör olarak görev yapmakta. Kendisi birçok ülkedeki üniversitelerde önemli araştırma merkezleri de kurmuştur. Yine çok sayıda bilimsel derginin de kurucu editörüdür. Hocamız güncel olarak 6G, terahertz iletişim, nesnelerin interneti gibi alanlarda araştırmalarını sürdürmekte ve anahtar yayınlar yapmaktadır. Aslında söylenecek çok daha fazla şey var ama ben daha fazla uzatmadan sözü kendisine vermek istiyorum. Vereceği değerli bilgilerden dolayı şimdiden kendisine çok teşekkür ediyoruz. Ümit ederiz ki pandemi süreci bittikten sonra kendisini Trabzon'da ve Karadeniz Teknik Üniversitesi'nde ağırlayabiliriz. Sorusu olan arkadaşlar sunum sırasında mesajla sorularını yazabilirler. Sunum sonunda da hocamız soruları cevaplayacaktır. Katılımcı arkadaşlar sunumun sağlıklı ilerleyebilmesi için lütfen mikrofonlarını kapatmayı, kapalı tutmayı unutmasınlar. Evet hocam, tekrar şeref duyduk katıldığınız için. Çok teşekkür ederiz. Buyurun, söz sizde hocam.
Thanks a lot, Tuğrul, for organizing this webinar. I thank the participants for listening to. You will have tons of information the next 60 minutes. I hope you can follow me and you will not be bored. So I will talk about 6G, but actually it's 6G, right? So everybody is now jumping on the 6G. So a lot of things that I sent you, it goes more to the 7G and beyond, by the way. So you see here a perspective from 5G to 6G. Now, because the 5G is already well established and others are already deploying the 5G systems worldwide. And we put the last 18 months a lot of effort to write this paper here, which in IEEE Access Journal in July 20. I just have to warn you, there are many papers, even from Turkey and from many countries. People are writing papers on 6G. So we have more than the other paper covering, so which you will see on the next slide. But anyhow, so I want to put the evolution from 5G to 6G. For example, the peak data rates are expected from 20 gigabit per second to almost 1 terahertz, as you say, in 6G. In 5G, we have peak spectral efficiency like around bits per second per hertz. We are expecting that will jump to the 60 bits per hertz or seconds per hertz. And then end-to-end latency, the objective is 1 millisecond. To my knowledge, the operators can reach now 2 millisecond end-to-end latency, but this is really optimistic value, like mostly like around 10 millisecond end-to-end latency, but the actual expectation for 6G will be 0.1 millisecond. So you can see the requirements are really challenging. And then the cell edge data rate, we are talking about 0.5 gigabit for 5G. And in 6G, we are expecting 1 gigabit per second. And the end-to-end packet error rates, in terms of reliability, we have this at the -5 for the 5G, and in 6G, we are expecting 10 to the -9. And the mobility, the support for mobility is around 500 per hour. And we are talking about, again, more than 1,000 plus kilometers per hour expectation. So you can see The requirements are very challenging, and also the objectives, and hopefully we'll be able to achieve these in the next several years. So in this paper, I mentioned to you that we have more than many other papers are covering, especially some of these areas. I have been conducting research the last, say, 10, 15 years. So unfortunately, it's impossible to cover all of these subtopics. So, for example, the 5G has this softwareization concept like SDN and FE, and that will continue in 6G, but in more network automation in terms of slicing, for example. And I expect also reconfigurable front ends. That means these front ends should be able to access from very lower frequency bands, say 1 gigahertz, up to like 1 or terahertz bands, seamless access to these frequency bands. You can imagine that design will be very challenging according to the antenna design, right? And of course, dynamics sharing, right? So these spectrums, we should be able to be available to all us seamlessly. We should be able to access these spectrums between very low to very high frequency. And everybody knows this AI and machine learning will play a major role. It's already playing a major role, but in 6G it will take more and more. But you know, my vision on this AI ML, I remember in the 80s we had this AI, millions of dollars or even billions of dollars were invested in the US and Europe. It was, you know, it died down, but now it's coming back again. But I think we should really raise minds and come up with something new, not like, you know, this classical neural networks and deep learning, same old stuff. Instead, you know, can we make the brain like neurons and how the brain is working and then mapping to the machine world, right? So that's a fantastic challenge, right? So there is even a brain initiative in Europe for €1 billion to understand the brain, and so that would have a bridge from the brain to the you know, to this our MI machine and AI world. Instead, you know, tons of people are just doing these classical algorithms. I you know, honestly, that will not bring us to anywhere, in my opinion. So backscatter communications, and also since we are using cell-free or the SDN and FE type softwareization with these controllers, we are getting out of the cell concepts, right? So all these base stations will be software driven. It will be like cell-free communication. And then also we'll use MIMO or massive MIMO communications, as we already know. And then you see to the end, there is no order, but I will start about this seminar with terahertz band. So we have to go to the higher frequencies, and then you will see that terahertz has problems. One of the biggest problems is the distance. So how do we combat the distance problems? And then I will present you the intelligent communication environment, or they call it also reflecting intelligent surface, RIS. Like, the world is crazy. I mean, really sad, but we'll see. I will talk about those. Now, hundreds and thousands of papers are being written every day. And then Internet of Space things with CubeSats and AVs. And then also with all these, we start with Internet of Nano things, nanoscale machines. And I will also a little bit about for health applications, especially with all these diseases, that will take a bigger role. Internet of Bionanothings, the concept that I introduced years ago. So I will mention some issues there, and with quantum communications. So you can see these dotted areas are mostly for the NG, you know, more, and the others are mostly for 6G coverage. And I don't do research on quantum communications, but I believe that it's really very important, and it's interesting to look into that, but it will also be part of the 6G, right? So we start with nano things. So let me motivate work. I started back in 2006 because nanotechnology was taking off, and I went through the micro technology back in the 70s and how it changed our lives. And then I thought the same way, these nano machines, nanotechnology will change our lives. And then I started to work on, if these devices are out, how will they communicate, right? So that was the notion. And then I came up with this idea, which was like 3 years ago. One of the companies in the world, although US hates them, they invited me for a strategic planning meeting in New Jersey. And so I came up with this slide I want to present to you. So now, currently we have these, all these smartphones, laptops, desktops, everything, right? And then we have all these wearable smart watches, smart ring, anything you can imagine, right? And then also virtual assistants, now Alexa, like Echo, right? Siri, right? And so when our grandchildren, maybe I will not see it, because look at yourself, people. You look back 25, 30 years ago, you say, my God, your desktops were so big. Your laptops were like from the Stone Age, right? So our grandchildren will tell us this thing about us, about these times, saying, why the hell do you have all these desktops and iPads and iPhone, all those things? Why? Can't you do everything automatically, right? So now, in other words, this Alexa will be the primitive start, by the way, or Siri or Echoes, you know? So I'm going that direction, saying, can we do something without any of these devices? Right? Everything will be automatically, right? So remember the Star Trek movie or the TV program? It was always interactive, right? So now, so all these devices are not practical, like devices, battery powered, then they are not natural. Sometimes the voice cannot be understood, remember, like the accent and all that stuff. Something to Siri, she doesn't understand you. Limited functionalities, as you have seen in the home or office environments. So I want to change this thing, right? So I want to have everywhere, outdoors, outside, inside the persons, by the humans, right? And they should be susceptible to the user naked eye. Because when you have all these devices around you, like Bluetooth sticking out, come on, it looks awful, right? So I always curse at them if you are carrying those things, right? And they should be user-friendly, and all this accents should be understood, and they should be smarter. They should be self-powered, right? So how will we do all of these things, right? And so we go to environments of. I called that many years ago, nanoscale machines or things. And you see that with all these platforms, right, you will be able to put them anywhere you want, right? They will be acting like your interfaces or relays or whatever you call them, right? So like access to any backbone network, backbone desktop, or your laptop, whatever you want, right? You don't need to carry anything. Your sends everything. And then you can also have these bio-nanoscale machines inside the body. That's another thing. I will explain that to you. It can also monitor your health issues, right? Inside and also outside, but they are invisible because they are very small. And then you will always interactively, communicating. You will have nanophones here, visible, also nanophones in your ear, and then you can say, like now you say, find the restaurant, right? It finds. Why do you need to hold that damn thing, or it should be around you, right? Say, I need, for example, my mails, or what is the latest file, or what is the latest football result, right? Something like that. So all of these, like voice-driven and more automatically, and then we are also writing, we have this paper actually, this will be another big issue in my opinion, with all my colleagues from Greece and Cyprus, Internet of Metamaterials and their software enablers. So that will appear in the TU journal. So it took many years to get to this. So I will explain you more of these things. So now, when I was presenting these scale things, Internet Nano things, many people said, "Oh, this is really science fiction, etc." Really, I had many interesting events, actually, memories. But in 2016, Scientific America, they just announced, remember, that they're endorsing Biden, right? So that's the scientific. So they put this top 10 emerging technology as Internet of Things goes, right? So remember, I started in 2006, and then here is a lately report in May, at the end of May 2020, and they are talking about the marketing the ground worldwide. All these companies that you see there are betting on nanoscale machines and their Internet of Nano things, right? So we were right. So you can imagine, right? So we had this design of nanoscale machine, right? Because there was nothing, and like almost years ago, you can see that some of these components exist though those times. So now, because we wanted to create these machines and they should communicate with each other. So, for example, nano memory, nano processors, nano energy harvest, nano transceivers, antennas, actuators, and sensing units, right? And then they should be put into very, very confined, small platforms. So then we start this research, as I told you, back in 2008, and I got a lot of funding from NSF, U.S. Army in the United States, but I also started a center in Finland under the FIDI program, Finnish Distinguished Professor Program. I got Alexander Ford Award in Germany. I started a center in Barcelona, so Nano N3CUT, Nano Networking Center, and they're all existing, right? So there will be like 60 people working on this subject, by the way, within my centers, right? So what we try to do is, first of all, we realized that these nano transceivers and nano antennas were missing those. And then we start to work on those from the design perspective. And then we observed, because we use these graphene-based materials, I will talk about it. And then we observed that graphene's patch on a dielectric material worked the best in very high frequencies. That ended up in terahertz, right? And then we realized that entire terahertz channel, like all these communication aspects, were virgin territory. So we did all this research. And then also, these file layer solutions, new module technique, synchronization, equalization, all of that. And then also all these protocols are missing. So, as I told you, the check marks meaning that we have the solution. And then, still in the meantime, of course, many other research centers and people start to work on these. Nowadays, there are many workshops and conferences, special issues. That's really took a wildfire, right? And then also initiatives in different countries and community, like, for example, Age 2020, when they announced it, the upper bound in the gigahertz, we were laughing, And now, of course, they said this was a mistake. Anyway, so let's continue this. So now let me talk to you about this nanotechnology that enables the control of the matter in atomic and molecular scale. And at this scale, the material people observed some properties that they were not observed in the micrometric level. So then they realized that they said, can we exploit these materials and their properties and accordingly develop new devices and applications? So that's the nanotechnology started. Actually, the starting point was back in 1959 with Richardson. He never used the word nanotechnology, but he has this famous speech. There is a plenty of space at the bottom, meaning on the nanotechnology level. In 1965, he received the Nobel Prize, and he was one of the finest scientists of this. If you never heard of Richard Feynman, it's really a shame. You should instead of knowing Ibrahim Tatlıses or some other people, right? So anyhow, so one atom. So what is the? Here's another invention that is called graphene. Atom-thick planar sheet of bonded atom carbon atoms in a honeycomb crystal lattice. That you can see here, it's so thin. That's why they think the people say it's like 2D crystal. Everything is 3D, right? It's like less than 1 nanometer thick. It's like honeycomb crystal lattice, right? And nanomaterials like this, graphenes can take different forms. Graphene nanoribbons here, graphene carbon nanotubes, or fullerene or buckyball. You know, you can do any forms with these materials. And the inventors received Nobel Prize in physics, Gaiman, Novoselov. In fact, end of September, there was this PMRC conference, or PMRC or PMRC. I gave a keynote speech the end of September 2010. I mentioned the guys will receive Nobel Prize maybe in 5 to 7 years. 2 weeks later, they announced that they received this Nobel Prize. So it was really fantastic. I was very happy for them, of course. They were born in Petersburg, and 2 Jewish guys, and they moved to Manchester, and they're professors at the University of Manchester, and they are also the leading people in the graphene ship, like €1 billion investment from the European community about graphene. Since like at least 5 years they are working on it. Leader is Andrea Ferrari from the University of Cambridge, but they're playing a major. In fact, Putin gave them an award, but they didn't go back, and they declined to receive the award. So because of this anti-Semitic and all that stuff, right? So graphene is first 2D crystal ever known, atom thick, world's thinnest and lightest material, strongest material, harder than diamond, 300 times stronger than steel. Take any form, bendable. They conduct electricity much better than the fiber and copper. Transparent material. They have very good sensing capabilities that you can use. These sensors have fantastic sensing tasks. And moreover, although I'm talking about information technology, like all these processors, memories, etc., but these graphene can be used for anything, right? In the future, you can have like aluminum, remember these plastics. Similar way, we can create airplanes, cars, refrigerators. Even you create these shirts for the police force or military. So you know it's a very large of applications. Of course, why don't we do it now? It's the costs. Like 1 by 1 meter, good quality costs like $3,000-4,000, right? So there is I love the word malzemeci. Material people, what the name, right? Malzemeci. The material are trying to reduce the cost, right? The malzemeciler, football meciler. Anyhow, so let's continue. So like there are these. Remember, I gave you this device. So there are already existing these nanosensing units. And then chemical nanosensing units or biological nanosensing units. They can do all these sensing of the molecules or antigens and antibodies. So that's already existing. Also nanopower generators like my colleague here, ZL Wang, zinc oxide nanowires he has, as you see here. And they're, from trembling, they can harvest energy. They're also nanowires, right? And then we also suggested, we got a patent, but then we didn't continue that. So can we use also the graphene, like as you see, it's sitting on a dark material, and then create this nano power or nano battery, and so that we will have these battery and transceivers and antenna based on the graphenes. And then the nano processor is already existing. For example, the Gaiman Novoselov, back in 2008, they showed the world's smallest transistor, like 1 nanometer at University of Manchester. And all these new laptops, like all of them, already have 32, 22, 14, or 10 nanometer transistor technology existing, okay? So now, can you imagine with all these, we can go to operating frequency close to 1 terahertz. compared to the few gigahertz now, like, I just bought a desktop. It's like 3 gigahertz from Apple, right? So we're talking about like a jump in the future with these nano processors, right? Nano memory, as you see the name also, Richard Feynman. So the objective is in nano memory, store a single bit in a single atom. So in Richard Feynman gave an example. He used to give all these homeworks. You find him in YouTube, by the way. Feynman lectures, a very interesting fellow, physics lectures. So anyhow, so he gave in these homeworks like 5 by 5 atoms were used to store a single bit in order to inter-atom interference. So that means 125 atoms fit. So now we are talking about single bit in a single atom, right? And there are these biologically inspired computing people, right? Looking at the DNA. DNA uses 32 atoms per bit. Again, far away from single bit in a single atom. But thanks God to them and some other companies, they use these golden particles or gold nano memories like here. And then, they have these tracks. And then they can store a single bit in a single atom. And then you can have terabytes information stored in this very small 10 nanometer scale memories. Like, these nano memories, a primitive way of these nano memories in these iPhones. So now, as I told you in our study, because all these components were already existing, not the antennas and transceivers, that's why I was interested in communication per se. So we developed these graphene-based plasmonic nano antennas you see here. So now the patch antenna is put on dielectric material, and graphene supports the propagation efficient radius of this surface plasma parton waves at frequencies in very high frequencies, catch. Because when you go lower frequencies, the radiation is not that efficient. And then why? Because these global oscillations of electrical charges at the interface between this graphene dielectric material, and then it's just gliding, okay? So he applied for a patent, and then CIA put a block for 3 years on this because they didn't allow it. And then finally they released in 2017, we got the patent. And then this work afterwards, actually, also plasmonic nanotransistors based on the high electron mobility transistor concept, HEMT, and we received the patent, applied afterwards after antenna, but we got it in 2016, 1 year before. So now at the end, we had this complete end, right? The antennas and also transceiver and all the other components are existing already, and then we needed to put them here and create these nanoscale machines, right? So we observed that once we started to communicate, and because I explained you why with this graphene, we observed that they work the best in very high frequencies, and we had terahertz band. So you see my former student that's at Northeastern, and he's in Shanghai Jiatongji. We did a lot of research the last 10 years or 11 years, actually. So then we put these papers together, like pointing out the the researches and directions for terahertz bands. And so then we received this, as I told you, these projects, and then we investigate the terahertz channel, and then all these other solutions which I will present to you now, because that time brand new. So for terahertz channel, we developed a new path loss model and noise models, 100 gigahertz to 10 terahertz band. And now I don't show you the math because the math is already in this in transaction wireless com. And so I just showed the lessons we learned. So when we have these nanoscale machines and working in very high frequencies, this is the problem. Like here, when you go beyond 1 meter, the path loss is so bad, like all the red areas, you cannot have meaningful communication. And so this is limited. but then the gain is huge, right? We are at terahertz level. But we also observed, I will tell you also why we have this problem, right? We also observed there are some windows, as you see here, these yellow areas, and that the distances can be much longer than 1 meter. So see that we will try to use those, because if a system is distance limited, we use them, right? So why are they distance limited, right? So let me give you the reasons. Again, when you have some experience in the 60 gigahertz, like millimeter waves, the oxygen particles is the enemy for signal propagation. When you go to higher frequencies, the water particles in the air become the enemy. So when these water particles affect the propagation, and that's why the distance are limited. So try to find other ways of combating this problem, right? So we said that, can we look at this multi-path use? You can see also Ozan Biçen'i series, now a professor at Sabancı. And so work with Chang to look at these multi-pass issues, because multi can help us, positive effect or negative effect. They help us for extending the distance. Yes, they did. Maybe not the full solution, but at least we could expand the distance looking at from the multi-path perspectives and using their advantages. So then there was also another issue about how to use the classical modulation techniques. So we came up with this full femtosecond long pulse spread in time. We call this time spread on and off keying mechanism. So when we had one, we had a very short pulse length. That's why we femtosecond long pulse. And then we had a certain time interval. We also optimize T of S, how long it to transmit the next bit, for example. So TS. And then when there was a zero, we had a silence. So that's kind of like a logical zero encoded as a zero. And then, of course, no energy is consumed in zero. But then you need a perfect situation between transmitter and receiver, because if there is a silence, so that the receiver thinks, oh, it's a zero, right? So, and then this also helped us, multi-users, to avoid any interferences or collisions, because these femtosecond pulses are so short that you can have multiple users. The problem that they will be overlapping will be minimum, and also based on our optimization of these intervals. Then, let's look to the entire world. We were not the only ones working. There are other people working, companies, and also some research groups. And also at that time in the past, 8.15 terahertz interest group, they were looking 300 gigahertz to 3 terahertz. Actually, we contributed a lot those years. And then they wanted to move it to the IEEE standards group, but IEEE said, oh, this is too far out. And then they, like 100 gigabit per second, that's the frequency band they're interested in. So now there are many research challenges. Although working on this since many years, still a lot of issues that we are in computer science, like MAC protocols, routing, relaying. There are some floating around, but they are cheating the system, because they're just using classical routing, say, oh, this works for the nanoscale. That's not right. So we have to come up with some realistic solutions. Same thing with the transporters like TCP, etc. Like for the addressing is an issue. What should be used for the IP addressing, right? IP version 6, good luck. So the address will be huge, right? So how do we take care of like addressing, an association of the network service discovery as a part of the addressing, right? Security, authentication, data integrity, open problems. Now, my interest was the last 10 years also, in addition to those problems, about distance problem. How can I combat the distance problem? Moreover, each time I presented this work, a lot of operators said, what about lower frequencies, right? Because they want to make money out of this. So I also looked at lower frequencies. And of course, the distance problem relates also to the non-line of sight problem. So for the lower frequencies, we realized that if we change our materials from the graphene to like metamaterials, for example, then we can go to lower frequencies, number one. Number two, after talking to these flagship Ferrari, Leonardo Ferrari from University of Cambridge, he told me there are these new graphene structures like molybdenum disulfide, also hexagonal boron nitride, okay, and then also like this hierarchical nanomaterial stacks. And he says that they are fully developing these materials, and they believe that they will be able to operate in lower frequencies in addition to the materials, right? So now about the combating distance problem. So now I wrote this paper with my student, and Shuaini, she's still here, but she will graduate soon. She will be a new assistant prof in the US. She wants to stay here. So we try to explain how do we combat distance problems raised in terahertz band. So remember I said that these windows. So we looked at those sub windows and try to, because they are longer. So we said, can we look at those windows and create distance adaptive modulation, meaning add them and then use only those sub windows, right? And it helped. Didn't solve the problem, right? And then another issue was come up with new concept of the massive MIMO, MIMOs, but with newer ideas. We call this ultramassive MIMO. And then the intelligent walls concept, right? Reflectable interface. Now you see how I ended up there, right? So now I'm just going to the ultramassive MIMO. As you see here, also got a patent for it, 2017. So I talked to you about these nano antennas. So now we are putting 1024 by 1024 antenna array elements, and in a very small area. And then that's why we call it ultramassive MIMO. And again, graphene, and it's sitting on top of the dielectric material. And we did a lot of evaluations. And then also we came up with, this dynamic way of using these massive or ultramassive MIMOs. For example, subsets can have different beamforms, right? And then they can all work together, and they can create single focus or razor sharp beam. In fact, last week and also morning after my Abu Dhabi meeting, we had Army meeting, and this new notion in the defense. It's unclassified work. It's called directional networking or directional communication. Please don't say directional antennas. There's nothing to do with that. It's more like this type of beamformings, but intelligent way and razor sharp of those related problems, right? So here are the massive MIMOs, right? Here you have multi-band bands, kind of like heterogeneous frequency bands, and you can use them in a heterogeneous ways, right? And there are many challenges. I mean, again, Shuaini, the girl is working in her PhD on all these things. Like, for example, how to accurately estimate channel coefficient, because there are so many antennas, right? The spatial correlation problems, and how do we estimate thousands of these parallel channels, and how do we operate these antenna arrays in these different modes I showed you, right? And also, how do we control optimally each array element? How do we design a code book? And then how do we these beamforming, beam steering, and then like directional communication? So these are all question marks. So I hope that this terahertz and Internet of Nano things, and I would like to the intelligent communication environment, because that will all help us to extend the distance. Plus, the initial idea about all these platforms everywhere, these platforms, to realize these intercommunications, right? So that will help all of that, right? So now you see a bunch of Greek names here, right? So actually my name this also, but it's as you know, last name, right? Akyildiz. So people think that with all these Greeks and Cyprus people. Yeah, so please don't ask the reason. I know these people, especially Andreas, since maybe 30 years, like he's a brother from South Cyprus. So we start to work on this 2015 when he came to my birthday party. That was my 18th birthday party. No. Anyhow, so then also my keynotes and nano things. And then he presents some of the ideas, and then I said, oh, it's junk. And then we worked and worked. And so these other people are working in the Kriti, Girit, Fourth Research Center, FRTH. So now we have a lot of papers and all that stuff, and we developed this fusion tech effect project. I will come to that. So we have patents. So now, in the meantime, as I told you, the entire world is like going crazy on this. Even in Turkey, people are writing, and all these names are out there. You know, people call different names. Intelligent communication environment, intelligent communication surfaces, reconfigurable intelligent surfaces, all of that. Right. So it's like crazy. You know, really. Again, you know. So anyway, I will mention my opinion about this type of. So now, why do we need intelligent communication environments? I give reason for the distance and also my overall, you know, the view about this interactive communication. There are also many other useful advantages, right? So first of all of you in the communication, thanks God we have these problems, right? So that we can make money and theses and papers and to bring bread to our home, because all these electromagnetic waves or all the communication wireless domain has these problems, right? Shadowing, reflection, scattering, absorption, path losses. Thanks God, right? Into problems. And then people, since decades, we try to mitigate, solve them, this and that, but we cannot solve them, right? That keeps trying to solve them, right? So, and also distance problem, as I do, coverage problem, energy issues, etc., security. So now all these people in the world are working on aspects like, you know, attacking these problems, like adaptive antennas, MIMOs, massive MIMOs, distributed MIMOs, beamings, right? All of that, you know, people keep writing, right? And get, you know, solutions, and, you know, operators are using them. MAC and routing protocols, and they are successful, but they do not solve the entire problem, right? And it's like kind of white, right? It doesn't get rid of those problems. Thanks God, we should continue to, right? So plus all this random channel behavior screw the performance, right? So now I also mentioned to you about distance. Now that's another issue, right? Now, so when we started to address this distance problem, I told you about, you know, like distance adaptive modulation, then ultra MIMOs, but also we looked at these mirror concepts those years, 2011, 12. And then there's this reflect arrays, decades that are existing, right? And these reflect arrays, all they do is they'll hit this surface and they will be reflected. There's no processing, nothing. Just reflected like a mirror, right? And then there is this relay, right? So you can have these relays, and then you have these, you know, store and forward process, and, you know, and then hop. But the problem is, remember I gave you this, now you see why I gave all this reason. We are talking about end-to-end latency should be minimum as possible. As soon as you put these relays, each relay will introduce latencies, right? So that's not the best way of continuing to the relays, so that, because they will introduce longer delays. So more the backhaul infrastructure are costly, plus they are not flexible. And so the people try to come up with these intelligent communication environments. As I told you, again, I will be very quick. You know, there are, you know, I gave keynotes along this topic, so I could cover a lot. So now you can see here these patches, okay? And then there are these switches, like here. They could be pin diodes or varactors or MEM switches. In our design, it's called nanocontrollers. They can be either one or values, right? And then there are these microcontrollers or FPGA design little computers. And then there are these coding sequences, like codebook in the Mimos, right? Different states of these patches can take. So that will be application. So now some people use wired between this and here, or some people are using wireless, and some have different sizes for these, right? There is no or standardized sizes. What these platforms can do is they can convert the passive in wireless environments, right, to intelligent communication environments. That means they can do all these functions, right? They can do control reflections of the signals when they hit on the side, as you can see. They can reflect, or they shifting, polarized reflections, columnites, speculations, splitting, focus, absorption. Why? Because these also metamaterials, we will also show that to you. Using those materials futures can realize these. So that's a fantastic idea, actually. And why, people are discussing about how we can use, in indoor and outdoors, like here in museums, indoors and also outdoors for, vehicle networking, or in the malls. I mean, the use cases are really very large, right? And then here's another use cases that you use them for physical layer security, because you can do intelligent formings. You can avoid unauthorized users or droppers, because you can have all these beamforming through these platforms, right? And also you can do even power transfer. You can use for particular users to satisfy their strict quality of service requirements. They're active, right? So then there are additional benefits. You can optimize beamformings and spatial diversity. You can do a much more sophisticated way of resource allocations, especially with these slicing network function visualizations, like in spatial, spectral, and temporal criteria to do resource allocations. You can track mobile users, etc., etc. Right? So maximize data rates. As I told you, the world is going crazy with these topics, and majority of the people, you will see that, again, went through the papers, I don't know, like thousands of papers there. Most of the signal processing and communication people, I don't appreciate, actually. They do not understand the surface internal functionalities, really. Okay, this is this box. I go in here, it comes out, and from signal processing, information flow, etc. Come on, guys. So that's really not the way to do it. But some of these guys feel good teams, because this needs a large team. You cannot do 1 or 2 or 3 people and saying I'm doing this. Maybe you can do part of it. And now you can see all of these, pull out some of them, and I cannot go through them all of that. Each has different functionalities, and then each of them have different bands and purpose and dimensions, like size of these surfaces. There is no optimum size or standardized size, as I told you. And like our project is called Wiser Surf, is, to my knowledge, maybe the largest group that we worked on the 3.5 years. And here is the project. It took us 3 times because it was 3% acceptance rate. And so it's called Wiser Surf. The Prof is leading, and University of Cyprus, Center in Catalonia, Signal Generics, Aalto University, and Fraunhofer Institute from Berlin. So we had this consortium. It was like 6 million or 7 million. Here, 6 million euro, but we had also additions. So again, this was like huge team. The device, hardware people, physics people, biology, chemistry, computer science, electrical engineering, mechanical engineering, the fabrication people in Fraunhofer, name them. So they're all here. So this was the meeting last year in Crete. Actually, some of in the toilet in the time. So you can see there are all these bunch of young people. I'm here. So this guy was from European Community, a manager, listening to us, and fantastic team really. And so all this research, like design, build, and trade. And then work packages, like, Europeans always have these different work packages, fundamentals, understanding the EM case, the antenna case, the programming cases, hardware design, assembly evaluation, also prototyping, fabrication, and also like theory studies, right? So now it's going fast. So what are the novelties here? So there is this material that has these intrinsic functionalities. That's what we use. Metamaterial means beyond, which is a material engineered to have a bit that is not found in nature. So you can manipulate electromagnetic waves, like block, absorb, enhance, and waves, in order to achieve benefits which go beyond is possible with classical materials. And their shape, geometry, size, orientation, and arrangements gives them intrinsic intelligent properties. And that, you see, this is a hardware, a picture actually, that is fabricated. I will show you this again to you. So now you can see here that the schematics of this cell, what they can do is that they can do instantly re-engineer the electromagnetic waves in, automatically do all of these, steering, absorbing, etc. Right? So that's the thing that we are using for the metamaterial-based surfaces, right? And here is the pattern that we are talking about. Again, I can explain you many details here because I want to finish, more stuff to present. So now you can see here, we call them tiles, and these meta atoms, and they're on the fifth meta surface layer. Well, we also have programmable surfaces. So then we are looking like programmable metamaterials, and then we call them hypersurface because we can then program them, right? And then that's the one that before, like FPGA or microcontroller. That's the device that can go back and forth between them. And then we have also these nano controllers here, right here, and we can achieve the operation of these surfaces. So now this is the 1 meter by 1 meter by the Fraunhofer tube. So they told us that it was one of our meetings, it cost 400 euro. These are the classical materials, right? We also, in the meantime, and then also we have both lower frequency bands, and we use graphene for the very high frequency bands, right? So they are, but these hardwares are so sensitive. So we had some demonstrations in some conferences. We could not fly them because they're not working properly after you fly, because they're very sensitive. But anyhow, so we are making them robust. So now there are many open research issues, right? So like resource allocation algorithms, scheduling algorithms. Then also we need to design them for futuristic areas. Like if you have a very large number of devices, how can we incorporate to like 5G and 6G, etc. I will come back to it. So then specific more research topics like fault tolerant. For example, if some of these patches do not work, can we forget the tile or this surface, or can we still operate them, right? Here, multiple surfaces. Where should you put these? Right? Control. So like you have a building or you have a highway, how these things we need, right? Again, the signal processing people just keep papers or networking. Here, one box, I go out. Come on. So now here is multi-hop, right? So you can do multi-hopping. That's not easy, right? So also, if you have multi-users, and how will you take care of and users and multi antennas, right? So now it's more real and more complicated, but it's too complicated. Don't go there now, right? So all the open issues. So now here are the bridge the gap between theory and real world deployments. Now it's time. People wake up, oh, that's interesting. Let me write more papers. But now let's start to look at real world deployments. Like at least show that, look, we can do better Wi-Fi applications at indoors using these surfaces, right? Right? So anyhow, and also can we use AI and more smart tools to make them much more sophisticated, right? And moreover, I told embed them in the IEEE 11. Also in the future, like how should we do 5G embedding, 6G, etc., right? IoTs, and then power issues, right? Frequencies and bandwidth and all this, right? They're all open questions, and of course standardization, right? So after all of these things, I want to also share this DARPA news. It was like 6 years ago and still active. They said there are 4 DARPA projects bigger than the internet. So one of them is atomic GPS clocks, atomic clocks for the GPS. And another one is wireless shield for Internet of Things. And third, another is rapid threat assessment. And you can see here, right? We started back in 2005. Terahertz frequency, electronics, device, metamaterials, and communication. So we were at the right track, right? So now a lot of people are working on those, okay? So now let's at another one called Internet of Bio-Nanothings, right? So here is this work that I did with my former student, Massimiliano. He's now a professor in Nebraska, and I created the center in Finland, as I told you. We're professors there, and we wrote this paper. Named this Internet of Bio-Nanothings, but the idea started many years ago, right? So you can see inside the body, we have all these neurons, hormones, calcium signals, bacteria. They really communicate with each other, right? So now the question is, can we create artificially designed bacteria, artificial designed neurons, right? So like these little devices, nanoscale, or molecular motors, and then inject inside the body. And then they can work as additional, calcium signals and hormones and molecular motor. And they can observe, monitor, because they can be programmed, human health. If there are problems, they can try to attack them themselves, or they can use these surfaces like 2-type nano devices. You can put them, they're invisible outside of your body, one or multiple. They can use your cell phone, near field communication. They can send through the internet to your physician. Physician can reprogram them, right? So that's the basic idea about nanothings. And I thought this is, this guy, Paul Ehrlich, he was from Wien. He had this idea about magic bullets. It's called Kugel in Germany. So he had this idea like 100 years ago. He received a Nobel Prize in medicine. So you are already these magic bullets. I'm talking about these engineered device scale machines, right? So now you can see that they will have also effects on each other. Like bacteria has effects on the molecules or hormones or vice versa. They need to be somehow captured inside the body, right? So we need to analyze them. And then also we have to have this this big picture cyber physical system, which we call it PARA. That means remedy for everything. So the interesting case, like 3 o'clock in the morning, I got this idea, istiare. No, it's not istiare. So panacea, and then also Reamer, meaning explorer. So explorer, these are these devices that I'm talking to you about, genetically engineered devices. And Fatih here, professor at Georgia Tech, Sarol, that's wrong, anyhow. Then Tevhide and all this Ülken, all these guys on this hardware design. And then also looking, like getting the information out to the cyber system, right? Cyber, and then, you know, the application will be early detection and mitigation of infectious diseases. Now here, because this started 2016, and we got, you know, our focus was mostly on the bacterial diseases. And then last October, I applied for Radian Science and Technology Project for the Medical Rijks University Hospital. And we got first like 1.5 million euro. And it was announced. And now everybody's jumping on COVID, etc., you know. Here, detection and mitigation of infectious disease, right? But I have to, our case was for bacteria, but then we are you know, discuss how we can use it for the viruses, right? So now the last part was on the cubes. So I have like 3 or 4 more minutes to use that. It's another subject that I strongly believe that these IoT space, right? So we are talking about in 5G, like 50 billion machines, right? So like trillions of machine-to-machine communications. So now I also believe that space segment will be also playing a major role. So now here are some papers that, okay, why I started this work was I did a lot of research for NASA in year 1996 until 2005. A lot of geos and, you know, MEOs and geos and deep space internet. And like, you know, one of my former students, Eylem, had a lot of work on the Ohio State now, senior prof. And then, you know, a lot of work, and I went out 2005. In 2017, I went to University of New Mexico. There is an Air Force lab, research lab. And then they told me about these CubeSat. I was interested, and I started to work on it. And as you can see here, it took us 1 year to get some vision on that, and also got a patent, like it will be issued now very soon. So what are the disadvantages of those conventional lights? It takes very long. Development and deployment cycles, almost 7. It has high construction launching costs. For example, Hitami telescope failure had $300 million lost. 10 years of research. I don't want to go to the Iridium, for example. Almost killed the, I mean, it really killed the Motorola, right? Iridium. What is a CubeSat? Actually, all this high technology is like done 10 schools in the university, right? In the US. But now, like California, you know, California Polytechnic Institute, no, I'm sorry, California State University, Cali Poly, it's a teaching institute. That was in 1999, it has this CubeSat idea. I'm really, you know, respecting him that he had this idea. So these are very small, like they have the unit, 1 unit meaning 10 by 10 by 10 centimeters, like a mug size. If you have 3U, 30 by 30 centimeters, right? So it's very, you know, it's easy to divide, you know, hard. In fact, I was serving on the European Community C grants. There were some couple young guys in America, they applied for this. So some people are doing research on CubeSat. Okay, I don't remember even their names, right? So there are interesting ideas about CubeSats, right? Advantages. Now, so all these things are existing, right? Like these internal organs, but I wanted to from a different angle. So now my angle will be in the communication, right? So now that's the, you know, how I entered it. Also, there are all these existing companies, like Tintin is the, you know, the Elon Musk, Rin Tintin, I mean Tintin Specs, and they have, you know, already some deployment, and some other, you know, Australia, Switzerland, US, they're already in place. But what they have is all limited, you know, and then also limited frequency bands. I can see. And also the data rates are low. And then mostly they cover certain areas and then no coverage, right? They move and they come back. So I want to have a generic solution, right? That's one. So like all this space segment, but also I had some ideas. So one of the ideas is, so I want to show you without going details. So now I realize that terahertz, because there are no atmospheric effects in the space, there will be no problem. So I can operate these CubeSats in terahertz, right? Long distances and very high bandwidth between these CubeSats, number one, right? And then number two, going up and down, I wanted to use these reconfigurable front-end idea. That one of the challenges, right? That will be like this front-end dynamically, any lower frequencies to up to terahertz, right? So because, you know, there are atmospheric effects, I cannot just operate them in terahertz, right? That's another novelty. And the third novelty is like 5G, actually, everything softwareized. There will be no software on these. All the software will be in these controllers. STN and FV is done the ground segment, right? So that's those are the knowledge that I had. Like you can see here, the design as well as the STN and networking case. Our design is 3U and 5 kilo maximum. And then we can use multi-frequency transceivers and multi-frequency antennas seamlessly. And all of that are the antennas, they can flip over, right? Open up and all that. Then you can see all of these frequency bands we can use seamlessly, right? And then this is the STN and V base where the centers are, okay? And this is the suggestions for the controller design, the softwares and mono tools, etc., right? And there are many research issues. I mean, like hardware, the software design, all of that, right? So, and then also you get some machine learning algorithms. So I thank you. I'm a little, actually a couple of minutes above the time, but I told you so many. I hope your brains are not burning now, as I try to present so many forms, and I don't know, some of you say, what the hell is this, right? So I hope that you got the points, and hope some of you will be interested in research on this. And my advice to you is, before I go to Q&A session, that work on, young people. I hope that there are many young people here. Don't take all problems and write another paper will care, right? I mean, it's wasted time. If you say, oh, I just PhD, but that's, you know, it's sad, because you must have an impact, right? Impact is that people will recognize you and your work. They will give you references, and you can be proud of saying, I did this. Not papers, you say, oh, I have 200 papers, look. So what, right? We are not here in the paper writing business. So do not complain there are not problems in telecom. There are many, many problems. And hopefully you will be working on these. So I'll be glad to go through questions and answer them. There are some. Let me see the chat. There's nothing here. Wow. So Tuğrul, you can take over.
Evet hocam. Çok teşekkür ediyoruz. Çok güzel bir sunum oldu. Çok harika bir sunumdu. Bayağı verimli oldu. Çok şey öğrendik hocam. Bir de yani çok geniş konulardan da bahsettiniz. Soruları olan arkadaşlar mesaj yoluyla sorularını sorabilirler. Sorarken de hocam benim bir tane sorum var. Onu sormak istiyordum size.
You can ask Turkish. I hope I can understand the terminologies in Turkish, but I'll be glad to answer in Turkish. If I can, I will see.
Evet.
Or you can type them if you are shy.
Hocam siz programlanabilir Meta Surfaces tasarladınız ama bunları planar yani düzlemsel olarak genelde resimlerde gördük. Dolayısıyla bu düzlemin, bu plane'in önündeki elektromanyetik dalgaları genelde polarize edebilir gibi görünüyor. Bu polarizasyon açısından...
Sadece polarize değil, bir şey yapabiliyor.
Biliyorum hocam. Absorbe ediyor, bloke ediyor, frekansını süzüyor vesaire. Bu servis edebildiği açı aralığını daha da arttırabilmek için düzlemsel değil de böyle omnidirectional olarak, yani dairesel olarak bu yüzeyleri tasarlamayı düşündünüz mü? Belki daha fazla açıda elektromanyetik dalgalara servis yapabilir bu yüzeyler.
Aferin, bravo, iyi soru. Aferin. Şimdi all this work is still progress, right? That means we're talking about flat platforms, and then also the size to be determined, and also the performance and multi-hopping and all of that. But now I also there a paper that it will come out. That will be another major breakthrough, in my opinion. We call it metamaterial surfaces. So it's not just this that everybody does this thing, right? It's much more. So you can create any shapes. You can put them on fabrics, in your furnitures, anyways, etc. And so it goes with your direction, actually. We already started that, and it will come out. But that, I mean, by the way, these are concepts, right? So you can, right? It's not like we have a solution. We are like discussing those, and then we also point out many open resources, right? So if you want to get into that topic, you can start with that, right? So looking at different shapes of these surfaces, right?
Evet. Çok teşekkürler hocam.
That's a good
Başka
question.
sorusu olan arkadaşlar
There are some
varsa.
questions.
Evet.
There's a guy, he put a smileys. What the hell is that? Oğlum ne demek istiyorsun orada? Smiley face koymuşsun oraya. Oğlum. Muhammed Talha Kakız, o öbür çocuğun adını söylemiyorum. Yani what the hell is that? Be professional. As far as I understand about Internet of Things, material problems come first before communication problems. Maybe after real nano-intelligent devices will be developed, problems may change. Do you think material solutions affect communication? Of course, but you see, Muhammad, that, you know, the nanomaterials are already in place, right? I told you that like graphene is in place, and then also metamaterials are in place, nano zinc wires in place, okay? It's not like we have not, right? So given that we already have those graphenes, and then even when we have this new hybrid type of graphenes, they will help us to go to lower frequencies. For higher frequencies, we already showed that communication problems can be solved with our line of the transceivers and antennas. And if you want to do, you know, another material that somebody will come up, that's another issue, right? We're not talking about that. So anyhow, so your question, you know, material is in, but it's not like we are expecting that materials will develop. They already developed. So we just use the graphene, and really very important material, and it works. So now now this guy, which company do you think is the closest to achieve the broadband communication? I personally heard about, but nothing more. What do you mean by global broadband communication? In which, what do you mean by global broadband communication? In what? All of the above, all the paradigms, or what do you mean by global broadband? Okay, let's go to the next one. You can specify what you are trying to say about broadband communication. In the long term, quantum computing will change the rules of the communication due to the nature of quantum world. Yes. Entangled quantum particles will play the most important role in, yes. Will to use propagation means such as wires or air? Yes. What are the major charges there? Your opinion? Okay, so that's truly true, but that doesn't, okay, that quantum will take over and we will just replace everything. That's not the case, right? They will, you know, you will have certain islands, like the entire networking area, internets will have these space domains, right? So based on some applications, use cases, the security is the most important part. You can use the quantum part, and the rest could be like classical communications. And of course, you will have some gateways in between quantum world and classical world, right? So for the challenges, go through the paper, right? So you can read more about all the quantum challenges, because I told you that I have to pull out all the slides and go them. So, you know, one of them is, of course, like the gateway. So the gateway meaning how will you marry the quantum world with the world? But there are many other challenges. I mean, here's an example. Let me ask. If you're a physical layer guy, okay, try to understand the quantum channel, really. So realistically, right, quantum channel and the wireless domain. There are some papers, but I don't think they're for the time being. And then also validate them with the practical applications. Good luck, right? Practical applications. So that's, you know, I would suggest from physical layer. And then, of course, all these other things like error control and the modulation, some of the techniques, can they really help us if you have a real large quantum network? I don't know. Or another issue that I remember is the protocols. Like one of my former postdocs, Marcello Calais, he's in Napoli. I did a lot of work with him on the cognitive radio 10 years ago. So he's very active now in the quantum communication. He gives tutorials and papers. Check the site. You can read more. He has even some routing papers, but in my opinion, the area is really open right now. Anyhow, so what else? Sure. What is the global broadband communication? He will say, oh, does he know what global broadband communication? No, I don't know. Can you explain? What do you mean by global broadband? I mean global internet provider. What do you mean by global internet service provider? Come on, guys. So you say you think that one guy, Elon Musk, will have global internet service provider? Come on. No. What do you mean by global internet service provider? Yeah. Talk to your operators. We have some people maybe from some companies and explain the server issues and, you know.
Evet.
Anyhow.
Başka sorumuz olan var.
So one person or one entity, one company will not own everything if you're trying to talk like, you know. So you have to understand internet concept first and then question. Okay, go ahead. What else? Please ask. How many people do we have here? Only time you said there will be many people.
40'a yakın kişi izledi hocam. 40'a yakın. Biz bunu YouTube kanalımıza da koyacağız. Bölüm YouTube kanalına da koyacağız hocam. İnşallah daha fazla kişi
That's fine. I mean, I don't care. It's not the quantity, right? Quality of the people. Anything else? I thank you for listening to me. And I have to run to another meeting now with Navy now. Sorry, guys. They already started like 20 minutes ago. If you have any questions, please send me an email or ask Tuğrul. Tuğrul can forward them to me. And or if you have questions about future research directions, all I'm asking is please do not duplicate known results. Do not waste your time with old problems, and then don't say I have etc. Work and put all your, especially young people, for the impact. Right? That's the question. Impact. You know, what can I do? Let's say, let's take a name here. Baturalp Günay, for example, right? It's an interesting name. So say, you know, what shall I do that the world will know about Baturalp's work, for example, right? That's the impact I'm talking about, right? So Erkan is asking me again, expected deployment of the usage of meta surfaces. Remember, I told you the generation, like 6G. So I expect, that's hoping that people will do that research, right? Deployments and things. So I'm hoping that, you know, in the next 5 years, we will seize them, right? So that's the objective. Like in my Russia, I have this support from Putin and neuroscience. We're also working on those with Huawei, Moscow there, and 6G. So we are to do this for the indoor cases, Wi-Fi. So hopefully, I don't know, we'll see what I can do there, right? And there's in Greece or all the European community, we have some cases that hopefully will come up. More questions? Okay. So, and I think presentation and also the paper that I have, and there are other papers on G, they should give you an idea what are the open resources and, you know, work on those problems. And another that I recommend young people is when you do not find any paper, don't say, oh, there is nothing. I'm happy that there is nothing, because you will be the first and people will give you references. That's the way you make it. If you find 100 papers, you say, oh, let me tweak here and there. That's a waste of time, right? So be happy if you don't see something, right? Okay? So, anything. Okay, good now, guys, okay? Thank you for listening to me.
Hocam biz teşekkür ediyoruz. İnşallah en kısa zamanda pandemi bittikten sonra sizi Trabzon'da ve üniversitemizde ağırlarız.
Ve lahana ve de balık hamsi.
İnşallah hocam, inşallah. Yeter ki şu pandemi bitsin. Çok teşekkür ediyoruz hocam. Saygılar bizden hocam. Sağ olun. İyi günler dileriz.